Welcome back, everybody. So now we're going to see another application of compactness, and the idea now is to show that a certain notion, okay, connectedness, is not definable. Okay, so up here is the same definition we had before. Graph is just a bunch of vertices with edges connecting them. The edges are represented by a binary relation E. 2 points are connected if there exists a sequence of vertices that have edges between them that connect one to the other. And what we want to prove is that the connectedness relation is not definable in graphs. Okay, so connectedness relation, let's call it C, inside a graph will be, for each particular graph, we're going to have a different connectedness relation, and it's a set of all the pairs of vertices in the graph, right? Such that V and W are connected. Okay, and saying that this relation is not definable, we are saying there is no formula such that with two free variables which exactly defines this on every graph. Okay, so what we're saying is there is no well-formed formula phi with two free variables, x and y, two free variables because connectedness is between one point and another. It's a relation such that on all graphs, let's call them V, domain V and edges E, we have, and all elements V, W in the graph, we have that V and W are connected if and only if it is true that this formula holds in this graph about these 2 points, V and W. Okay, so it's no formula phi that is going to be true about a point V and W if and only if V and W are connected. So there is no way to define connectedness in a first order way. How are we going to show this? Well, you can guess, by contradiction. Suppose there is such formula x phi of xy, see? And what are we going to do? Well, we're going to do something similar to what we did last time. We're going to create a set of sentences, and we're going to use compactness on it to derive a contradiction, right? We want to get a contradiction by assuming that such a phi exists. So what are we going to do? We do the same thing as last time in this case. So we let tau be now the vocabulary of graphs together with new constant symbols C and D, same as last time. C and D are constant symbols. And now we are going to consider the following set of sentences. And what are going to be the sentences? First, axiom of graphs. Let's call this guy up here AG for axiom of graphs. And so T is going to have axiom of graphs to say that something is a graph. And then we are going to add the sentence that says that C and D are connected. So this is the phi that we just are assuming it exists. And it says that C and D are connected. Okay. And then we're going to add all the sentences phi sub n from the previous slide that say that there is no path between C and D of length length n. Okay, so this sentence comes from the previous slide and is right here. Let's copy that. Okay, so phi n says there is no x1 up to xn such that they are formal paths from C to D. And again, we want to show that every finite set of this, I mean, this as a whole is not satisfiable, right? This is just very easy to see because on the one side we're saying that C and D are connected. Supposedly this formula phi is defining connectedness, so this is saying that they are connected. And on the other side we're saying that there is no path from C to D of length n, and we're saying this for all n's. So actually there is no all these sentences together are saying there is no path, and this one alone is saying there is a path. So you cannot have all of these together at the same time. There's no way. Okay, so this should not be satisfiable. So let's apply compactness backwards this time just to change the form of the argument. So if the whole thing is not satisfiable by compactness, there is a finite subset T0 including T0 not, right? Because otherwise, if there wasn't such a T0 that is not satisfiable, if they were all satisfiable, then T would be satisfiable by compactness. So there has to be one that is not, but we get a contradiction from that the same way as we got before, right? So we just so there is an N0 such that T0 is a subset of AG union phi CD union phi sub n less than or equal than 0, right? If T0 is a subset of all of these and it's finite, well, it might contain this one, it might contain this one, but it can only contain finitely many of these guys. So there is a bound on which one it can contain, and then T0 has a model. Is satisfiable by the same model that we have in the previous slide. The same model we had before, we have that C and D are connected. So this is a graph, so it satisfies the axiom of graphs. C and D are connected, so it satisfies phi, and they are not connected by any path of length less than n0, so they satisfy all of these guys. So T0 is satisfiable, but we are assuming it's not, right? So that's our contradiction right there. And the contradiction started from assuming that there exists a phi that defines definability. Okay, so it cannot be the definition for defines connectedness. It cannot be a definition for connectedness in graph. An idea is, so let me just explain essentially what's going on. To say two things are connected, you have to say there exists a path of some length. But in first order logic, all you can say is that there exists a path of length n, like that's a sentence that we have right there. There exists x1 up to xn, which form a path, but we cannot say for some natural number n, because the natural numbers are not part of the structure, so we cannot quantify over the natural number. So we cannot say there exists an n such that in the natural number such that there exists a path of length n, because there exists an n, the n part is not part of the language, and even say a path of length n for a general n is not something we can do. We can fix an n 1747 and draw the sentence that says there is no path of length 47, and it's going to be a string of symbols of some size, I don't know, 250 symbols fixed, and then for each number 250 we're going to write a different sentence. We can put all these sentences together in a set, but we're going to have one sentence that says them all in first order, and that's what we're proving here. For connectedness, we need to use this infinitely many sentences. There is no single sentence that is going to define connectedness. Okay, we'll see another application in the next video.